Yes, sir. No. So chemical equilibrium. We've always said that A and B can react to form C and D, but what if C and D can react and form A and B as well? All right. Here's another example of a chemical reaction that is in equilibrium that we've introduced before. We have this. This is an acid. We remember it's an acid because it begins with a hydrogen there. This is the acetate ion. I don't know if you remember that business, but here we have acetic acid. It's a weak acid, right? It's not one of our strong acids. And so when a weak acid interacts with water, a hydrogen is pulled from the weak acid to the water molecule, forming this H3O plus and leaving behind the acetate ion. However, because it's a weak acid, that means it doesn't dissociate completely, and the actual amount that it dissociates is very small. So here's a chemical reaction that occurs, and these are the products for it, but the products will find each other and go back relatively quickly. All right? And so we want to have the ability to discuss these kinds of reactions and do calculations to know exactly how much of these different materials will be in presence or in a container in a reaction like this at what we call equilibrium. Okay. Now, the way that this reaction is drawn, we've said that the stuff on the left are our reactants and the stuff on the right are our products. But in reality, you can think about the reaction in reverse as well, because the reaction in reverse occurs just as much as the reaction going to the right occurs. So, dynamic equilibrium means that these things don't stop happening once you get a certain amount of your product. The product and the products are constantly reacting to form the reactants, and the reactants are constantly reacting to form the products. So that's called dynamic equilibrium. Once you reach equilibrium, the concentrations of all of these components, the two reactants and the products, the concentrations will stay the same. They won't change. But it's not because the reaction stops occurring. It's just because the reaction going to the right is occurring just as fast as the reaction going back to the left. Okay? So, here's an example where we just chose a single compound that's going to decompose into two of these. And if we plot the concentration of our N2O4 over time, it starts here, it decreases, but then at some point its concentration remains the same. Now, once its concentration is the same, we might be tempted to say, oh, so N2O4 has stopped reacting. Is that true, Sarah? Has N2O4 stopped reacting when we've reached this point here?
No. I'm guessing 2NO2 is just reacting at the same rate.
That's right. That's right. The N2O4s are still reacting and forming the NO2s. It's just that the NO2s are forming the N2O4 at the same rate. So the concentrations become stagnant. They don't change, right? But the reaction is still in dynamic equilibrium. All right, so let's see if we can learn anything from this video.
When heated in a closed system, calcium carbonate will decompose to form calcium oxide and carbon dioxide. As the amounts of calcium oxide and carbon dioxide increase, a reverse reaction occurs and calcium carbonate is resynthesized. When the decomposition rate of calcium carbonate equals the synthesizing rate of calcium oxide and carbon dioxide, the system is said to be at dynamic equilibrium. Now suppose most of the carbon dioxide is removed from the system, and the system is resealed. The rate of synthesis of calcium carbonate from calcium oxide and carbon dioxide will slow down and almost stop. However, the decomposition of calcium carbonate to form more calcium oxide and carbon dioxide will continue. As the level of carbon dioxide increases, the reverse synthesis of calcium carbonate will again begin. Eventually, the decomposition reaction rate will equal the synthesis reaction rate, and equilibrium will be reestablished.
All right. So we see there that you can do different tricks on your reaction, right? You can remove some of the product as it's being formed, for example. And because there's less product, the rate of the reaction going backwards will be slower, because we just went over a whole chapter saying that how fast the reaction proceeds, either to the right or to the left, depends on the concentration of the materials. And so if you remove the concentration of one of the materials, you'll shift the equilibrium. The concentrations of everything will have to shift, but eventually equilibrium will be reached again. Okay. Now, we want to have a way to express in a single number information to people about an equilibrium. All right? So here's a chemical reaction. I'm showing it to you. There it is. This says if you put A and B in a box, in a fixed container, then A and B will react and begin to form C and D. C and D, because of the reverse arrow here, will begin to react, and C and D again will begin to react and form A and B again. Okay? But just because I write this equation, it doesn't mean I know how much in my container. See, I'm talking about my box, right? Just because I tell you that this is the chemical reaction, I started with A and B in there, it doesn't tell you how much of the different components, how much of the A, how much of the B, how much of the C, and how much of the D will ultimately end up in the container. All right? So it's nice to have this statement because it tells me, yeah, A and B can react to form products, products can react to form the reactants again, but we want more information so that I can give this and a little snippet of information to tell somebody about the relative concentrations of these once equilibrium is reached. All right? And we don't talk about this kind of reaction going to completion because the reaction will never be in completion. It's in dynamic equilibrium. Okay? And we have a number. We have a number that can express in a single value the relative concentrations of the different components, and it becomes helpful to us for understanding how these reactions proceed and how to best perform them. Okay? So, here's an example. My reaction, A plus B to form C plus D, they can come back the other way as well. The coefficients of A and B and C and D, written as little a, B, C, and D there, I can write what we call a quotient for this reaction by simply putting the concentration of C times the concentration of D over the concentration of A times the concentration of B, or the concentration of the products over the concentration of the reactants, where all of the concentrations are raised to the coefficient for that concentration. So this quotient then is a value that can help us know about the chemical reaction right away. So for example, if I have this chemical reaction here, and I say K equals 10,000. K equals 10,000. All right? Or, sorry, Q. We want to start off with Q. Q equals 10,000. Q equals 10,000. Well, right away, because I know, oh, the quotient, what they're talking about is they're talking about the concentration of the products over the concentration of the reactants raised to their exponents, to their coefficients. And if this value is large, like 10,000, then what that tells me is that, because this is a quotient, the products up here, reactants down here, it tells me that at equilibrium, there's a lot more product than there is reactant. So once this reaches equilibrium, inside the box, you're going to have mostly C's and D's. right? Mostly C's and D's, because again, the quotient here, 10,000, tells me that most of it is product. All right? Different chemical reaction. For example, E and F coming together to form G and H. All right, so I have a different chemical reaction here. And if I tell you that the quotient for this value is 0.003, all right, the quotient for that value is 0.003. What does that tell us? Melissa, what does that tell us in terms of what will be in the box if I combine all these if I combine these two reactants together?
Well, aren't they constant?
What's that?
Like, I thought we just said that since it's a closed system, all of it will be constant throughout the whole time.
That's right. These concentrations won't be changing over time, but when equilibrium is reached, this value, this 0.003, is telling me that the concentrations of the products raised to their, no, over the concentrations of the reactants equals this value. So what is going to be higher, the numerator here or the denominator, to get that number? The denominator. So that means the concentrations of E and F are going to be higher than that of G and H. Okay? So, go ahead.
How can the concentrations be at equilibrium if they're not equal?
Well, equilibrium doesn't mean equal. Equilibrium just means that the reaction going forward is occurring at the same speed as the reaction that's going in reverse.
Oh, okay.
We'll talk more about it. This is just the beginning. Let's practice writing our own. Well, let me tell you one more thing here. Q is, go ahead, Trace.
Oh yeah, so for example, the reactants, there was going to be way less of can you show the stuff on piece of paper you just had? So yeah, we're going to have way more reactants than products.
Yes.
So does that mean the products, because we were talking about equilibrium, so do the products, since they require less, are they just more reactive with one another, or?
That's right. That's what that's telling us. That E and F react slowly. E and F react slowly, but G and H, as soon as they appear, they react fast and go right back.
All right, sweet.
Okay. So, one more thing about this. The Q value, quotient, for any chemical reaction will be called K and is known as a constant for an equilibrium reaction when we are at equilibrium. So if we reach equilibrium, then the quotient will be given the value K. And notice that this is a different kind of K than the rate constant. How is it different, Jace?
It's uppercase?
That's right. It's a capital K. So the capital K, when you see that, it's talking about an equilibrium constant. Equilibrium constant. All right. So another name for these equilibrium constants is this quotient here is called the mass action expression. I like to call it just the equilibrium expression, but this is also a phrase that we want to become familiar with. So, can we write the equilibrium expression for this equation? The equilibrium expression, the quotient for this equation, right? Help me out here, Sarah. What am I going to write for the equilibrium expression for this equation? Q equals,
Q equals concentration of, oh shoot, the product.
That's
which is
right.
N2O4,
Uh-huh.
and then it's raised to 1, yeah.
Mm-hmm.
And then all of that divided by concentration of NO2 raised to the second power.
Very good. Excellent. Okay. Next one. That was Sarah, so it's Alyssa's turn. What do you think, Alyssa? What is the equilibrium expression for this reaction here?
Q would equal N or CO2 in the bracket over with the 2 as the exponent, and then divided by CO in brackets to the second, and oxygen O2 in the bracket
Okay,
to the 1.
to the 1.
If you want to put it.
Yeah, very good. So these are our quotients, and anytime we look at an equation that has an equilibrium, people can give us K values for chemical reactions, and what they're saying is that the K value will equal this expression. Okay, so take a few seconds, try to find the right answer here. Alyssa, no, that was just Alyssa, so it's Jace's turn. Jace's turn. Can you tell me which one of these is the right answer, Jace?
Yeah, let me take a look. Kind of throwing me off with the subscripts and the superscripts and stuff, but is it A?
That's right. It is A. Okay. So we knew that the concentration of products is supposed to be on top. We knew that the concentration of reactants on the bottom. But the 4 here has to go with this one. Right? This one doesn't have the 4 squared. This one has our concentration of our products on the bottom. All right. Okay. Very good. Excellent. So the numerical value for our K, which is our equilibrium constant, which is Q, the quotient, when we're at equilibrium. The numerical value tells us the relative relationship between the concentrations of the products and the reactants in an equilibrium reaction when it's reached equilibrium. Now that's a mouthful, right? But it's a very helpful tool to use and concept to understand. Because almost all reactions are in equilibrium, right? Till now, we've only talked about kind of the easy reactions to avoid talking about equilibrium. But there's very few reactions in biological systems or in nature that are not in equilibrium. Almost the majority of reactions can proceed backwards just as well. Okay, so the concentrations of our reactants alter the rate of the reaction. We know that from last chapter. Let me repeat that. The concentrations of the reactants alter the rate of the reactions. If we increase the concentration of a reactant, it will increase the rate of a reaction. In most cases, right? Sometimes it won't alter the concentration of the reaction. So for example, here's a chemical reaction that's reversible, all right? Silver ion comes together to form, or react with chloride ion and form silver chloride solid. Now you could say, hey, if I put in more silver ion, this reaction will go faster towards the products, and that's correct. Same thing if I put more chloride ion in a reactant, in a reaction as a reactant. It will proceed much quicker to the right if there's more reactant, right? That's what we just learned about. The rate of the reaction depends on the concentration of the reactants to some extent, usually, right? It might be a zero order, but not generally. However, the solid here doesn't alter the rate of the reaction, because if I put a little bit of solid or a ton of solid in there, it's still solid. So the amount of material that's available to go back this way hasn't increased. There's still plenty of material. So the rate of the reaction going to the left here does not depend on how much solid you have in your reaction. And so because that's the case, the equilibrium expression for this sort of a reaction, that's at equilibrium, will not include the silver chloride in the expression. All right, Sarah? Can you help us write the mass action expression or the equilibrium expression for this reaction here? What is Q going to be equal to?
Yeah, Q equals concentration of AgCl.
Okay. Now, what did we just say, though, about the concentration of AgCl because it's a solid? What did we say?
Something about it does not.
That's right.
alter the rate of the reaction.
That's right. So instead of putting up here AgCl, this is what we want to do, right? Because we just, proud of ourselves, we just learned how to do that. But because it's a solid, it's not going to be included in the reaction. We'll just put a 1 there to kind of take the place of it. But the rest, because they are aqueous, and as you change their concentrations, they will change the reaction. So where do those go in this quotient?
So those would just go on the bottom.
Okay, concentration of silver ion times the concentration of chloride ion. What are they raised to?
Just to the first power.
First power. Very good. All right. See that, Sarah, how we didn't include the silver chloride because as a solid, there's so much solid. If I put more solid in, it's not going to change the rate of the reaction. However, on the other side, if I put in more silver ion, the reaction is going to go faster to the right and shift the equilibrium.
So
Okay.
if the AgCl was aqueous, would it be different?
That's right.
If it was liquid?
That's right. So here's another one for you, Sarah. Can you give us the Q for this one?
Okay, yes. Q equals concentration of H3O.
Plus,
Yes, raised to the first power.
okay,
And then times the concentration of H2PO4 minus.
okay,
And that's all over a concentration of H3PO4 plus the concentration of H2.
okay. Now,
Or
what do you think because of our previous experience, what do you think about this one here? It's a liquid. What is that going to tell us? What do you think? Is it possible that we can change the concentration of water significantly by adding more water to this reaction? I'm not going to...
I'm going to guess no.
That's right. I'm not going to be able to change its reaction because there's so much of it already. I'm not going to be able to change its concentration significantly by adding more water. In fact, if you add more water, you just dilute the concentrations of the things that are dissolved in the water, right? So you do not increase the rate of the reaction by adding either a solid or a liquid. It's only when it's aqueous, which you can add more of then, and change its concentration, or gaseous, because you can always put in more gas and it'll increase the pressure. So, there is our quotient. That doesn't include the liquid. Take-home message, we don't include solids and liquids in mass action expressions or equilibrium expressions. All right, so, Alyssa, which one of these is the correct mass action expression for this reaction?
D.
D as in dog?
Yes, D as in dog.
Okay, good job. Excellent. So, we didn't include the calcium phosphate, the product here. Why not, Alyssa?
Because it's a solid, so changing adding more solid wouldn't change the rate of the reaction.
That's right. Okay, very good. Jace, do you want to take a stab at this one? What is the mass action expression for the reverse reaction?
Let me take a look. It's either A or B, but I'm not sure.
Okay. Want to help us out, Sarah?
So I think it is B because, or 1 second. So it's product over reactant. Yeah, so it would be B because the reactant in this case is the Ca3PO4, and that is solid, so it would not affect the rate of the reaction.
Okay. So, we were asked to give the mass action expression for the reverse reaction. And we had reactant as solid. The products over here were our aqueous. So the products go on top, and the reactant, which is a solid, is not included. Very good. Any questions about that, Jace?
Yeah, I had heard just the question before. I kind of got sidetracked for a second, asking my dad a question. But so whenever it's a solid, it's always just going to be act as like a 1.
That's right. If it's a solid
Okay.
or a liquid, like in this reaction here, we don't include the component in the mass action expression or the equilibrium expression.
Okay, and that's for whether it's like the reverse or just the normal.
Yes, that's right.
Okay. All right, thank you.
Yeah. Now, while we're talking about that, let's just have a quick little thought experiment. And let's see, Sarah, Jace just went. So Alyssa, you can help me out with this thought experiment. What is the relationship between, here's a simple chemical reaction, A going to B, all right? And here's another chemical reaction over here, where B goes to A. How will the quotients of this top one, we'll call it quotient 1, compare to quotient 2 for this bottom reaction, Alyssa?
Won't they just be inverses of each other?
That's right. So this quotient 1 will be equal to what?
The concentration of B over the concentration of A.
Right, very good. And this one will be the product, concentration of A over the concentration of B. So you can see that changing or flipping a reaction creates the inverse of the K value, or the quotient, right? Okay. One other thing here. The concentration, when we talk about a mass action expression or an equilibrium expression, concentration is in units of molar, all right? So this equilibrium constant, it's K now, so it's an equilibrium constant, is saying that the molar concentration of this substance, which is the products, squared divided by the molar concentrations of these materials, right? this one to the first power, and this one second squared. And this is the product here, not plus, right? We're multiplying these two together. And again, in the brackets here are showing that these are molar concentrations that we're doing this math with. If we're talking about P, then our materials are gaseous. And so we're talking about the pressure of these reactants. Or in this case, sorry, the pressure of the product, and these are the pressure of the reactants. Okay? So Kc is when you're talking about molar concentrations, and Kp is when you're talking about pressure. And there is an equation that allows us to go from Kp to Kc. This is an equation that's going to have to be provided to you, right? I'm not going to have you use brain cells to memorize this sort of thing. But what you would want to do when you saw this equation is a couple things. One, you'd want to be able to say Kc, that's talking about molarity. Kp, that's talking about pressure. Even if you forgot that, the R value would have to be around as well. And the R value here, liter atmospheres per mole Kelvin. Liter atmospheres is indicating to you that the pressure here is going to be in terms of atmospheres. The concentration here is in terms of molar, right? Temperature is involved as well. So that's going to have to be in Kelvin because we have Kelvin in our R constant value there. And all of this is raised to the change in moles of gas. So if moles of the product minus moles of the reactant, that value goes here, and we can take our molar concentration times RT raised to the change in moles of gas. So for example here, here's a reaction. Kp for the reaction is known at this temperature. What's the value of Kc? We can identify Kc by taking Kp and dividing it by our RT delta N. Kp is given. Temperature, 25 plus 273, 298, right? Did I say that right? 273, yeah, 298. R is our 0.0821, right? And then our change in moles would be moles of gas on the product side minus moles of gas on the reactant side. So this is 1 minus 2. So this would be a negative 1 to the negative 1 value. Okay? I'm not a fan of plug and chug, but that's what we'd have to do to solve that sort of a problem. And you know, I don't like to include these types of things. It might be there, but it would be provided in such a way that all that would be required is you to sit and look at the units and try to figure out what the equation is expressing. Okay, so like we said about reversing a reaction, when we reverse the reaction, the K is inverted, 1 over K. All right, and we did that thought experiment here, and that's not going to be hard for you to forget. If you just set up a simple thought experiment like this, you'll be able to see how K's for reversed reactions need to be treated. Let's do another thought experiment. Sarah, can you help me out with this one? Here's an experiment where I have A going to B, all right, and then I have C going to D, and I want to think about the relationship between these Q values and a third Q value. The third Q value is going to be A plus C going to B plus D. Right? Which is the sum of these two equations. Can you see it, Sarah? What is this going to be compared to these values? let's say I call this X and this Y. What is that going to be?
Yes. Sorry, I need to look at it for a minute.
Let's write it out the way we were before.
Yeah, that would help.
What is this one?
So it'd be concentration of B over concentration of A.
Okay. And this one?
That would be concentration of D over concentration of C.
Okay. What is this top one going to be?
Concentration of B plus, concentration of B times concentration of D over concentration of A times concentration of C.
Okay. So how does this compare to these over here?
It kind of looks like you just like put them together if you added them.
Did we add them? Or did we multiply them? Do you remember?
Yeah, multiplied.
We did, didn't we? Because if you take fractions like xy times z over b, that will be xz over yb, right?
Yes.
So when you add equations together to get a new equation, you can take their equilibrium constants and multiply them together. And that will be the equilibrium constant for your combined reaction. All right, so two different thought experiments that we introduced. One, thinking about the reversibility. It's the inverse of the reaction, inverse of the equilibrium constant. And when you add two reactions together, the result is the product of the two equilibrium constants. Okay? So, here's a reaction. What would be the Kc for the reaction that's provided here? Alyssa, you want to help us out?
What would be the what? Sorry?
The
KC?
the K, right? So if this reaction, N2 plus 3H2 going to 2NH3, has a K value of 500, what would be the K value for this reaction down here? Very similar reaction, but not the same thing, right?
Would it be negative 500?
Well, let's see if this thought experiment plays a role in that, right? Because isn't this reaction up here just the reverse of this top reaction? You see that, Alyssa?
Yes.
So how does the K change?
Oh, it's inverse, so would it just be 1 over 500?
That's right. 1 over 500, which is 0.002. Very good. So, Jace, here's another question. What would the Kc for this reaction be? The equilibrium constant for this reaction.
I'm not quite sure because, like, are we gonna have to solve for it using the equation for this one because we're not given the Kc like for the other one? Or
So how do these reactions compare? Let's see how these reactions compare. This one here, and then our third reaction here.
So it'd be 250.
Well, would it be 250? How would I get this reaction here? I would add two of these together, is that right?
Yeah.
Okay, and then we pull out our thought experiment. When we add two chemical reactions together, what happens to their Q's or their K's? It's the product, right? So I've added this this first reaction here to my second reaction, got the resulting reaction, and the K was the product of the two individual Ks.
So it would be like 250 times 500, or am I off base?
No, it would be this. So apparently, the K for this reaction times itself would equal the K for this reaction. So that's basically the square root of 500, right? Okay? Do you follow that?
Yeah, that makes sense. So if it was like 1/3 plus like 1/3 N2 plus 3 or 1 H2 over 2/3, would it just be like the cubed root of 500?
If it was 1/3, so you're saying if you're taking 1/3 of this reaction here?
Yeah.
Yeah, that's right.
Okay.
Okay. So that is a good place to stop. So what we've seen is we're introducing equilibrium reactions and ways to express information about those equilibrium reactions through our equilibrium constant and our equilibrium expressions, right? So like this equilibrium expression shows us how we would relate and relay information about the concentrations of the reactants or products at equilibrium. Okay, very good.